Finally, I'll conclude with a slightly different characterization of hypercontractivity, this constant SPXY, and I'll call this is an information theoretic characterization due to Chandran Nair. So I'll call this Chandran Nair's information theoretic characterization. I would like to remark that an earlier some of these results were already available in earlier work of Alsvede and Kach. From the 70s, and this is a recent paper from 2000, maybe 15 or so. I can't remember the year. It's a conference paper. So essentially what we will do is we'll connect hypercontractivity to so-called strong data processing constants in information theory. So suppose you have this input distribution Px and a channel W, then the strong data processing constant associated with this Px and W, well, we can just write it as the joint distribution Pxy. It's defined as max over all input distribution Qx that are absolutely continuous with respect to Px. The divergence between WPX and WQX and WPX divided by the divergence between QX and PX. Okay, that's the strong data processing constant here. And similarly, we can define the strong data processing constant for mutual information as sorry about this. Okay. As the maximum over all distributions PUXY such that PUXY has a Markov relation. So U can be formed only by looking at X is equal to PU given X PXY of mutual information between U and Y divided by mutual information between U and X. So we know that all these coefficients by standard data processing inequalities, that these coefficients are less than or equal to 1. And when this coefficient is strictly less than 1, we call it a strong data processing inequality. Okay. So it was shown by Alsvede and Gach . Sorry, I spelled it wrong. This is shown by this Alsvede and Gach that this strong data processing constant for KL divergence is actually equal to limit p going to infinity sp of not xy but yx. Okay. Yeah, there's an asymmetric treatment of x and y here, and this is the right order we have to take. Maybe, yeah. So that's what we define this SP in a particular order. So that's the order in which this comes in here. In fact, here also it's not symmetric in xy. This first coordinate is treated differently from the second one. First is the input and second is the output. Okay, so that's what it was shown. That's quite interesting. So this strong data processing constant gets connected to hypercontractivity constant, and later it was shown by I think Venkat Anantram. Uh, Maybe Amin Gohri and Sudeep Kamath, Chandra Nair. This is very recent, about 2013 or so, that this guy itself is also equal to limit p going to infinity sp yx. Okay, so these two strong data processing constants coincide. Okay, and what we will show now is a much more refined relation between strong data processing inequalities and hypercontractivity, which will recover all of these results. And this is the result due to Chandana. So what is that result? I'll just call it a theorem. So before I say theorem, I need some more quantities to be defined now. So define kappa for KL divergence, kappa p let's say yx, kappa p xy. It makes sense to think the way we define hypercontractivity. It makes sense to think of the first coordinate as uh, input as the basic random variable here, there, and in this definition, it makes sense to think of uh, the other one as the input, and that's why we have this sort of a um, switch in the order. Okay, so kappa xy is defined as max over all distributions qxy that have density with respect to pxy of divergence between py and qy divided by p times divergence between pxy qxy plus minus p minus 1 into divergence between oh sorry px and qx and px. Okay, the input output. This is also equal to max over qxy absolutely continuous with respect to pxy, the divergence between qy and py, just like the data processing inequality, strong data processing coefficient. But there's an additional term which comes, and that additional term is p into this minus this, so that's the divergence between qxy and qx py given x. Okay, that comes in. Similarly, we can define mu for mutual information p xy as max over all joint distribution puxy, not necessarily the ones having this Markov relation, of the output mutual information divided by p times joint mutual information minus p minus 1 times IUX. Okay, this is also equal to max for PUXY by this plus P into this minus this, which is just the conditional mutual information. Okay, so we introduce these two new quantities, kappa pxy and mu pxy, and if you take limit p going to infinity, then look at this expression here. The only way this expression, so if this guy is positive, okay, this is just a rough argument. Then as p goes to infinity, then this guy goes to 0, and therefore only way that you can have something more than 0 is when this is set to, as p goes to infinity, this also this thing also remains 0, and that means that you want py given x to be same as qy given x. Using this, what we can also see, I just roughly outline the proof that this guy in the limit as p goes to infinity is exactly the same as strong data processing inequality constant for KL divergence for pxy. And similarly, if you take limit p going to infinity and look at this quantity, once again the only way to get positive constant is to have this as 0, and this will happen if this is 0, then you can only look at those channels for which this Markov condition holds, and then it coincides with the strong data processing constant for mutual information. Okay, so this is true. These in the limit as p goes to infinity, these quantities coincide with the strong data processing coefficient. So the main result that we'll present is for each p, SP of yx is equal to kappa p of xy, which is also equal to mu p of xy. Okay, that's the main result that we have. So the proof is a little bit involved. I'll just give you the main idea. So what we will show is that SP of yx is less than equal to kappa p of xy is less than equal to mu p of xy. Okay, so let's show this part first. Oh, sorry, and this itself is less than equal to SP of yx. So for this part, this green part, this green inequality here, let r equal to SP of, sorry, let theta be smaller than SP of yx. Okay. Then there exist functions f and g such that expected value of fy gx this guy exceeds G P prime and F theta P. Okay, because it's smaller than the smallest possible, so this must exceed this. Note that without loss of generality, we can assume that both these norms are 1 because we can divide by these norms and define new functions, and this inequality must hold for that function. So, without loss of generality, assume that this norm equals to 1, and in this case, when we assume that, we must have fy gx, the expected value must exceed 1. Okay, this will show up as a constant in the calculation. We'll define it as c. Okay, so now we define a measure change. So we'll use these functions to construct this measure qxy that is used in kappa. So define, maybe before that, let's prepare a little bit for this definition. So consider functions f bar y given by f y to the power theta p and g bar x given by gx to the power p prime. Okay. And what we know is that expected value over y of f bar y equals to expected value over x of g bar x equals to 1. So this is by the assumptions that the norms are 1. And that expected value of f bar to the power 1 by theta p times g bar x times g bar to the power 1 by p prime this is x is equal to c, which exceeds 1. Okay, so we use these functions to define our measure change argument. So define to define a new measure qxy as, so we'll define its density. The density that q has with respect to p is given by f bar 1 by theta p y g bar 1 by p prime of x, and we need to divide by c. Okay, so that it normalizes to 1. Okay, so this is a definition of q now. Now let's compute all the quantities involved for this q. So let's say let's compute the denominator first, or denominator of kappa for this q first. So we have p times dqxy pxy plus minus p minus 1 times d qx px. this is equal to p times expected value log of this guy. So log fy f bar y to the y theta p, that's the first term here, plus p by p prime expected value log g bar x, and then p log c. Okay, this is the expected value of log of this guy. That's what divergence, and then this expectation is with respect to p, of course. When we don't write anything, the expectation is with respect to p. That's the bigger probability measure. And now minus p minus 1 times expected value of log dqx by dpx. Okay. So in fact, this guy here, this is equal to 1 by theta, expected value of log f bar y plus p minus 1 into expected value of log this g bar x by dqx by px. Sorry. So this one. So these expectations have to be carefully taken. All these expectations are with respect to qxy, and this one is again qx, because we didn't include the extra factor here. So again qxy. Okay, all the expectations are with respect to qxy. Minus p log c, that's what we have. And what we, so this c is greater than 1, therefore this guy is less than equal to 0. So since c is greater than 1, so we can just drop this. This is something positive we are subtracting. That part is this one, log f bar y plus p minus 1. Now let's look at this guy here. So this one is expected value over qxy log of g bar x by the Radon-Nikodym derivative of qx with respect to px x. If we take this expectation inside the log by Jensen's inequality, it will only increase the thing. Okay, so we get 1 by theta log f bar y plus p minus 1 log of expected value with respect to qxy, or just qx actually, it depends only on the marginal, so let's just say qx, of g bar x by d qx by d px x. But this expectation can be written as, so now let's look at just this part here. Just this part here. This can be written as expected value over px of d qx by dpx into g bar divided by d qx by dpx. Okay, this you can do where dpx qx by px is positive almost surely, so this cancels. So this is only expected value over px of g bar x. And what do we know about that? Well, what we know about that part is that the way we have normalized f bar, this is 1. So this thing is 1, and therefore this is log of 1, which is 0. So this is less than equal to, or this is exactly equal to 1 by theta expected value of qxy log f bar y. And just like this calculation, we can again multiply and divide by d qy by py, the log likelihood ratio, sorry, the Radon-Nikodym derivative for qy with respect to py, the likelihood ratio. We can do that. So what we get is 1 by theta expected value of qy log d qy by dpy. Okay, but this quantity again by Jensen's inequality, this is just the same calculations here, and because of the fact that expected value of f bar is 1 under p, this is 0 plus 1 by theta, and we can recognize the term here as a divergence between qy and py. So if you look at this, this is the numerator of the expression of kappa. This is less than equal to 1 by theta times the 1 by theta times the 1 by theta times the, that's the denominator, this is the numerator. So we get that d qy py by p into d qxy pxy minus p minus 1 d qx px is greater than equal to theta, which implies that kappa p xy is greater than equal to theta. And since this holds for every theta less than spyx, we must have kappa p xy greater than equal to spyx. Okay, this is almost complete proof. Some we have treated some soup as max and so on and so forth. In fact, we use max in a definition of kappa p. Should have used soup if you wanted to be more careful. All right. So we have shown this inequality here. Now let's show the other inequality, which is this one here. So the fact that kappa p xy is less than equal to mu p xy. Again, I'm showing this because these are very interesting bounds. Tell you about how divergence behave and how divergence how divergences can be related to mutual information. This is the next thing we'll show. Okay, and this is a very interesting proof. It's a nice perturbation argument. Okay. So suppose, because you were writing kappa as a max, although it's a soup, so this is a little bit informal, but that's fine. Suppose kappa p xy is attained by a particular distribution q. Suppose this is equal to this. We will use this distribution qxy to define a random variable u, which is used in the definition of mu xy, mu p xy. So how do we define that? So consider the distribution. Before that, it's a technical statement, I'm putting it here. Without loss of generality, we may assume that this guy here is less than equal to some large constant m, almost surely, with probability 1. We can assume that it's bounded. Okay, this boundedness will be used in our proof. Okay, so let's assume that. Now, with this assumption, we can define this distribution puxy, which needs to have the marginal of xy corresponding to pxy, as follows. So pu, so u takes the values 0 and 1, with pu of 0 is epsilon and pu of 1 is 1 minus epsilon. Okay, and where this epsilon is less than 1 by m. So this is the first part of the definition. Second part of the definition is pxy given the fact that u equal to 0 is the same as qxy, same as qxy. Then pxy given u equals to 1 equals to pxy minus epsilon qxy by 1 minus epsilon. So what does it mean? That is, this guy has a density with respect to pxy, and that density is given by 1 minus 1 by 1 minus epsilon into 1 minus epsilon times density of qxy with pxy. And since this density is less than or equal to m, this thing is always less than 1, and therefore this is a valid density. And you can also show that it integrates to 1 easily. Okay, so that's the second distribution. Okay, now, so this is a distribution that we have defined. Now let's define this function for a lambda for let's say theta again, theta less than kappa p xy, define g of epsilon as mutual information. So this u depends on epsilon, so I'll call it u epsilon. Okay, so it's the mutual information between u epsilon and y minus theta times the the denominator that comes up in the definition of mu. So I mu epsilon xy minus p minus 1 times I mu epsilon u epsilon x. Okay. So one thing you can check is that g of 0. So what happens when you have 0? Then under 0, this coincides, this distribution just has one value, which is pxy, and therefore the mutual information is just u is a constant actually. So this is just 0, 0, 0. So everything is 0 here. So this is 0. What about now the derivative of this guy around epsilon? In fact, we can comment on its derivative around epsilon in the limit as epsilon goes to 0. And it turns out that this is an observation from, I think it's from Chandra Nair's paper, but I think Chandra Nair attributes this to Gohri, and maybe it goes back further. So if you take this limit, this guy here, all these mutual information, they go back to divergences of the two perturbations used in constructing this UE. Okay, so these divergences are actually this limiting values for this mutual information, and this you can actually validate very easily by differentiating and taking the limit. So all the mutual information become the divergence between corresponding distributions used in defining this. Okay. And since we have assumed that, since we have assumed that theta is less than kappa, and this ratio, by the way, is kappa. Therefore, if we take this part out, which is the non-negative part, then you get some non-negative part into kappa minus theta, which must be strictly greater than 0. Okay, so here is a function which starts at 0 and its derivative is strictly greater than 0 at 0. Therefore, there exists some epsilon prime greater than 0 such that g of epsilon prime is strictly greater than 0, which in turn implies that, so this is greater than 0. What does it mean to have this greater than 0? Which means this by p by xy minus p minus 1 iu epsilon y is greater than theta. Okay, which in turn implies that upxy is greater than theta. Now, as before, we have shown that for any theta that's less than So we chose some arbitrary theta here. For any theta, where was my theta chosen? For any theta less than kappa p xy, mu p xy must exceed theta. Thus, mu p xy must exceed kappa p xy. Okay. Okay. So that this completes the second part. Okay. This is the second part, and both these parts were sort of self-contained analytics, so I could present them. However, this last part requires a lot of ideas from information theory. In fact, so that's why I'm calling this a sketch. So for this last part here, uses ideas from multi-terminal information theory actually. So I'll just tell you how we do it. We use the fact that this SP tensorizes. First, we use that mu p of xy is actually less than equal to mu p of xnyn. Okay, that's what that's true because x and yn has more options, and then we show that mu p of x and yn actually is less than equal to sp of yx for n sufficiently large, or in the limit as n goes to infinity. And that completes the proof. How do we show this last part? The goal is to use this distribution, this auxiliary u, which will be defined for, remember that there will be this u, you will have a joint distribution p, u, x and yn, and we want to use that distribution to define these functions which satisfy, to define these functions so that for those functions this inequality, the hypercontractivity inequality is violated. This holds in the opposite direction. Okay. How do we find these functions? Well, we actually construct functions as indicator functions of sets. Okay. And those sets, so we have to actually construct sets. And constructing such sets is a typical activity, is a standard activity, is a standard problem one needs to solve in multi-terminal information theory when we derive some coding theorem. So we use some typicality arguments, so-called typicality arguments, to define those sets. One more observation here is that while for a given xy, sp yx can be attained by must be attained by arbitrary functions, but sp x and yn for sufficiently large n can almost be attained by sets. Okay, so there is actually no loss of generality in using these sets. In fact, we show that this upper bound holds. Therefore, we show that for large enough n, it suffices to consider. It suffices to achieve sp y and xn. It suffices to consider indicator functions of sets, subsets of xn and yn, rather than this arbitrary functions. Okay, yeah, I went over this part quite quickly, but this one requires a lot more effort if you don't know these ideas from information theory. But on the other hand, if you know these ideas, this is a very elegant proof which uses some standard constructions from information theory to some typicality construction to show this inequality and exploits the tensorization property of SPYX. Okay, so this is the proof. So in summary, what we have seen in this lecture is we have defined this, we have started studying this Markov kernel, the conditional expectation, and we have checked that this Markov kernel is actually a contraction for any LP norm. And then we showed that when we defined this notion of hypercontractivity, when can Markov kernel be more than a contraction? When can this norm on the right side be less than P? And so we defined this quantity SPXY. Rather than finding when or what is this SPXY for a particular distribution, what we have been doing is trying to understand this question itself by expressing various equivalent forms. We saw that there's an inner product form which strengthens Holder inequality. Then we saw that this SPXY tensorizes. So this is equal to SPX and YN for independent and identically distributed X and YN, XI, YI. And we also saw the connection of this hypercontractivity, in fact equivalence of this with the strong data processing inequality for linear divergences. And finally we presented this is that equivalence, showing this for all q that have density with respect to p is equivalent to pq hypercontractivity. And finally we saw this alternative characterization in terms of divergence in mutual information. SPXY is equal to this kappa PXY is equal to mu PXY. By the way, once we establish this equality, this identity here, then by taking limit p going to infinity, both these results follow. Okay, clearly the strong data processing constant is equal to SPP going to infinity, and again both the strong data processing inequality constants are equal to this, and therefore both of them must also be equal. Okay, so this concludes this lecture. As I said, we haven't proved anything, any particular bound on SPXY or SPYX for any distribution. We have just shown equivalent form of this hypercontractivity requirement. In the next lecture, we will study hypercontractivity for Gaussian distribution, so-called Gaussian hypercontractivity, which was first shown by Gross. And remarkably, what we will show is that Gaussian hypercontractivity is exactly equivalent to Gaussian log Sobolev inequality. So this amazing phenomenon of hypercontractivity is also equivalent to, for the Gaussian case, is also equivalent to this super inequality called the Gaussian log Sobolev inequality, which we earlier saw was equivalent to Stamps